Complex and metal cluster. Metal pi complex 1. Content objective introduction. Classification of metal carbonyl. Classification on the basis of type of ligands. Classification on the basis of number of metal atom. Preparation of metal carbonyl from carbon monoxide gas. Reduct to carbonylations reducing agent plus carbon monoxide gas. From iron pentacarbonyl, dinuclear carbonyl from mononuclear carbonyl, mixed metal carbonyl by salt metathesis reaction. Property of metal carbonyl. General property, toxicity, magnetic property. Section bonding in metal carbonyl. Effective atomic number EAN rules. 18 electron rule. Counting of electron in complex. Determination of total number of bond in a cluster. Vibration spectra of metal carbonyl. Important reaction of metal carbonyl. Substitution reaction. Reduction nucleophilic reaction. Reaction with electrophiles. 8.5 Reaction with nitric oxide. Reaction with hydrogen. Transition metal nitrosa. Dinitrogen complex. Dioxygen complex. Tertiary phosphorine as ligand summary. Domino question. Long answer type question. Short answer type question. Objective type question. Answer to objective type question. Reference and further studies. Objectives. Objective of this unit are to introduce you with important and basic concepts to understand the bonding and structure of inorganic metal complex with some very important small molecules such as the carbonyl, nitroside, dinitrogen dioxygen, tertiary phosphosine as ligand. They are neutral ligands and are extensively used in the synthesis of inorganic complex in conjunction with other ligands. This chapter will take you through the detailed chemistry of metal carbonyl, including the electronic structure, bonding, synthesis, and some application. The chapter will also provide you with general understanding of other mentioned neutral ligands and their inorganic complex. Introductions. Coordination complex of transition metal with carbon monoxide. CO ligand are called metal carbonyl technically, and any coordination complex that has at least one carbon monoxide ligand in its coordination sphere is termed as metal carbonyl. Carbon monoxide is a weak level space. Even then, it forms stable complex with transition metal. Stability of metal carbonyls relies on the existence of back bonding between the metals and the carbon monoxide ligand. Since the ability of metal to participate in back bonding is directly related to the availability of electron density in its orbital. Hence, the stable metal carbonyl often compromises metal in their lower oxidation state. Metal carbonyl are used as homogeneous catalysts in organic synthesis and as precursor of the synthesis of other organometallic complexes. Metal carbonyl are used as homogeneous catalyst in organic synthesis and as a precursor for the synthesis of other organometallic complexes. Mononuclear metal carbonyl, that is those containing only one metal center, are usually colorless or pale yellow volatile liquids or solids that are flammable and toxic. Hence, skin contact, inhalation, or ingestion of metal carbonyl must be avoided while in laboratory by employing adequate laboratory techniques and safety equipment. Nitric oxide or nitrosyls ligands binds to metal in a very different manner than that of carbonyl. It is interesting to study the structure, bonding, and catalytic reactivity of metal nitrosyl complex. Define application as homogeneous catalyst in dimerization reaction, olefin disproportionation, and hydrogenation reactions. Furthermore, tertiary phosphosine PR3 ligands are one of the favorite ligands of inorganic chemists. This is because of a strong sigma donor and a pi acceptor property in their complex with transition metal. The electronic and steric property of phosphosine and hence their metal complexes can be altered as per need by varying the R groups, alkyl groups on PR3. They are capable of stabilizing transition metal complex in low oxidation state and hence considered an important class of homogeneous catalysts. We know that both nitrogen and oxygen are present in abundance in the atmospheric and hence they have become important raw material for large-scale industry synthesis of compound and the production of ammonia through nitrogen fixation. Nitrogen is reduced while reduction of oxygen gives energy. The electronic distribution geometries and bonding mode of these molecules as ligand in metal complex has been extensively studied and discussed in literature. Classification of metal carbonyl. The metal carbonyl are a class of organometallic compound where the metal atom is bound to the carbon atom of carbon monoxide, which is a small molecule act as a neutral ligand in this complex. There are several schemes to classify various metacarbonyls, some of which are illustrated ahead. Classification on the basis of type of ligands. Metacarbonyls are classified as homoleptics or heteroleptics on the basis of type of ligand present in the coordination sphere of the metal. Homoleptic carbonyls. The metal complex those contain only one type of ligand are called homoleptic complex. Hence, homoleptic carbonyls are those having only carbon monoxide molecule as ligand. For example, nickel tetracarbon monoxide, iron pentacarbon monoxide, chromium hexacarbon monoxide, dicobalt octacarbon monoxide, etc. Heteroleptic carbonyls. The metal complex those contain more than one type of ligand are called heteroleptic complex. Hence, heteroleptic carbonyls are those having carbon monoxide as well as other molecules as ligand. For example, nickel, tricarbon monoxide, phosphine, chromium, tricarbon monoxide, dinitroside, etc. Classification on the basis of number of metal atoms. Metal carbonyls are classified as mononuclear or polynuclear on the basis of number of ligands present in the coordination sphere of the metal. Mononuclear carbonyls. The metal carbonyl complex those contain only one atoms of metal is called mononuclear carbonyl. For example, nickel tetracarbon monoxide, iron pentacarbon monoxide, chromium hexacarbon monoxide, etc. Polynuclear carbonyl. The metal carbonyl complex those contain two or more than two atoms of metals are called polynuclear carbonyl. For example, dimanganese, decacarbon monoxide, diiron carbon monoxide, nonane carbon monoxide, dicobalt octacarbon monoxide, triiron 12 carbon monoxide, manganese cobalt tetramonoxide. The carbon monoxide ligand can be bridging or terminal. The bridging carbon monoxide has a bond order of nearly 2 which is similar to carbonyl in the organic compound, whereas terminal carbon monoxide has a bond order of 3. The IR infrared stretching frequency of 3 carbon monoxide is 2143 per centimeter. For terminal carbonyl, it is 2125-1850 per centimeter, and for bridging carbon monoxide lies between 1850 to 1700 per centimeter. Polynuclear carbonyl are further classified as homonuclear metacarbonyl or heteronuclear metacarbonyl, depending on whether the complex contains only one kind of metal or more than one kind of metal. For example, manganese cobalt nonane carbon monoxide is a heteronuclear carbonyl complex because it contains two types of metal with manganese and cobalt. Preparation of metal carbonyl from carbon monoxide gas. Treatment of carbon monoxide with the metals or their simple salt under condition of high pressure and high temperature yield corresponding carbonyl complex. For example presented below. Iron presence of carbon monoxide 200 atmosphere 200 degrees Celsius. Iron pentacarbon monoxide, nickel in presence of carbon monoxide 1 atmosphere 30 degrees Celsius, where nickel tetracarbon monoxide, cobalt in presence of carbon monoxide 1 atmosphere 30 degrees Celsius, we get dicobalt octacarbon monoxide, nickel Diiodide react with 4 moles of carbon monoxide. We get nickel tetracarbon monoxide and iodine. Nickel dicyanohydride cyanide react with 4 moles of carbon monoxide. We get nickel tetracarbon monoxide and C2N2. Reductive carbonylation reducing agent plus carbon dioxide gas. Treatment of carbon monoxide with simple metal salt in the presence of reducing agents such as hydrogen gas yield corresponding carbonyl complex. Few examples are presented below. Nickel sulfate react with carbon monoxide. We get disulfur H2 for 2 minor nickel carbon monoxide, tetracarbon monoxide. 3 moles of ruthenium ACAC3 is react with hydrogen. React with 12 moles of carbon monoxide. We get 200 atmosphere 150 degrees Celsius. Methyl alcohol we get Ru3CO12. Chromium trichloride react with aluminium. React with 6 carbon monoxide. In presence of aluminum trichloride density we get chromium hexacarbon monoxide solutions. 2 moles of manganese diiodide react with 2 moles of magnesium. React with 10 moles of carbon monoxide gas. In presence of diethyl ethers we get dimanganese decay carbon monoxide, 2 moles of magnesium iodide, 2 moles of cobalt sulfate react with 4 moles of copper and 8 moles of carbon monoxide at 200 atmosphere and 200 degrees Celsius. We get dicobalt octacarbon monoxide and 2 moles of copper sulfite. 2 moles of cobalt diiodide react with 4 moles of copper. We get 8 moles of carbon monoxide at 210 atmosphere 25 degrees Celsius. Dicobalt octacarbon monoxide 4 copper iodide. 2 moles of iron iodide react with 2 moles of copper, 5 moles of copper, 5 moles of carbon monoxide gas. At 210 atmosphere 25 degrees Celsius we get FeCO5, that means penta carbon monoxide iron, copper iodine, dicopper diiodine. Then 2 moles of calcium carbonate react with 2 moles of hydrogen, 8 moles of carbon monoxide. At 250 to 300 atmosphere 125 degrees Celsius dicobalt octacarbon monoxide, 2 moles of carbon dioxide, 2 moles of H2. Molybdenum pentachloride react with 5 moles of sodium and react with 6 moles of carbon monoxide. Diclime we get molybdenum hexacarbon monoxide and 5 moles of sodium chloride. There are some reports where carbon monoxide acts as carbonyl writing as well as reducing agent. For example, osmium pentoxide react with 5 moles of carbon monoxide at 350 atmosphere 250 degrees Celsius. We get osmium pentacarbon monoxide and 2 moles of oxygen. ReE2O7 react with 70 carbon monoxide at 350 atmosphere 250 degrees Celsius. We get Re2CO10 and 7 moles of carbon dioxide. From iron pentacarbonyl, the carbonyl groups in iron pentacarbonyl are labile and can be replaced by chloride to give a different metal carbonyl. Molybdenum hexachloride, we get 3 moles of iron pentacarbon monoxide in presence of diethyl ether 110 degrees Celsius. We get molybdenum hexacarbon monoxide 3 moles of iron dichloride and 9 moles of carbon monoxide. Tungsten hexachloride react with 3 moles of iron pentacarbon monoxide diethyl ether at 110 degrees Celsius. We get tungsten hexacarbon monoxide 3 moles of iron dichloride 9 moles of carbon monoxide. Dinuclear carbonyl from mononuclear carbonyl. Photolysis or thermolysis of mononuclear carbonyl yield by an multimetallic carbonyl such as diiron nonene carbonyl Fe2CO9. On further heating, the product decomposes eventually into metal carbon monoxide. 2 moles of iron pentacarbon monoxide. By taking radiation, we get Fe2CO9 carbon monoxide. Diiron, nonane carbon monoxide, carbon monoxide. 2 moles of osmium pentacarbon monoxide radiation. By taking radiation, we get diosmium, nonane carbon monoxide, carbon monoxide. Synthesis of higher osmium carbonate clusters such as tetraosmium 13 carbon monoxide, hexaosmium, octadecane carbon monoxide up to octaosmium tridodecane carbon monoxide can be achieved through the thermal decomposition of triosmium decacarbonyl OS3CO12 mixed metal carbonyl by salt metathesis reactions. 4 moles of potassium carbon monoxide tetracarbon monoxide RuCO3Cl22 2 RuCO2CO11 and 2 moles of potassium fluoride and 11 moles of carbon monoxide. Property of metacarbonate. General property. Metacarbonate are coordination complex of transition metal with carbon monoxide. They are also classified as organometallic compounds since they contain a metal carbon bond. Most metacarbonate are volatile, liquid or solid. They are colorless or pale yellow and are flammable. Vanadium hexacarbonate 70 electron metal carbonate is a bluish black solid. Di and polyatomic carbonate are darker in color. Triironodecacarbonyl Fe3CO12 crystals are deep green in color. Metal carbonate are soluble in carbon tetrachloride, benzene, acetone, ethane, glacial acetic acid. Toxicity. They are toxic by inhalation, ingestion, or skin contact. They carbonylate hemoglobin to form carboxyhemoglobin and it loses its ability to burn oxygen and form oxyhemoglobin. They are carcinogenic over long-term exposure. Magnetic property. All metal carbonate except vanadium hexacarbonate are diamagnetic. Metals having even atomic number from mononuclear carbonate having all paired electron. Dinuclear metacarbonate comprising of metals with odd atomic number have metal-metal bonds that utilize the unpaired electron. Thermodynamic stability. Metacarbonate are thermodynamically unstable when exposed to air. They undergo oxidation at different rates. Some are oxidized in air when heated. Structures and bonding in metacarbonyl. Structure and bonding in metacarbonyl. It is important to notice that there are not many ligands. Those from homoleptic complex like the carbon monoxide. Moreover, carbon monoxide is a neutral ligand with weak basic character that form stable complex with metal usually in their low oxidation state. In order to understand the structure of and the nature of bonding in metacarbonate, it is very important to understand the structure of carbon monoxide. Figure 5.1 represent a schematic molecular orbital diagram for the carbon monoxide molecule, where the middle shaped part represent molecular orbit of the carbon monoxide molecule, whereas 2s and 2p orbit of carbon and that of oxygen presented on the left and right hand side of the central shaded portion respectively. Now that the 2s and 2p orbit of oxygen are drawn at slightly lower energy level than the respective orbit of oxygen atom, which is attributed to the difference in their electronegativity. It is evident from the figure 5.1 that the highest occupied molecular orbital of the carbon monoxide is closer to 2p orbital of carbon. Hence, the carbon monoxide ligands coordinate through the molecular orbital. Molecular orbital primarily localized on the carbon atom, which suggests that the carbon monoxide ligand connect through its carbon atom with the metal center. Additionally, the molecular orbital diagram also reveals that there are vacant antibonding molecular orbital. Top 3 antibonding orbiter available on the carbon monoxide molecule, which makes up electrodensity from a suitable electron-rich species. Molecular orbital diagram of carbon monoxide molecules. 2s2, 2p2, oxygen 2s2, 2p2, 2p3, 2p4. So total electron will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electron will be there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here vacant d orbital, filled sigma, electron donating by carbon monoxide, sigma bond, M CO bond, electron donation by M, d pi p pi star bond, M giving electron to carbon monoxide back bonds. Molecular orbitals diagram of carbon monoxide molecule depict the formation of sigma pi bond between metal atom or ions and the carbonyl ligands. The upper half of the figure shows that the overlapping of HOMO localized on carbon with a suitable vacant orbital present on metal center resulting in ligand to metal sigma bond. It is an interesting fact. The formation of metal ligand sigma bond allows close proximity between the vacant antibonding orbital of carbonyl molecule and fill the orbital with metal center. Such proximity facilitates transfer of electron density from the orbital to the vacant ligand antibonding orbital, resulting in the formation of metal to ligand backbone. Transfer of any electron density from ligand to metal causes strengthening of ligand to metal bonds and make metal center rich in electron density, which in turn allow transfer of more electron density from filled d orbital to the vacant antibonding orbital situated on ligand and thus resulting in the strengthening of metal to ligand backbone. This phenomenon is called synergistic effect and eventually causes mutual strengthening of ligand to metal bond as well. Metal to ligand backbones. Metal to ligand backbone is an example of d pi p pi star overlaps attribute to the nature of overlapping orbitals. Effective atomic number EAN rule. The research state that total number of electron on the zero valence valency metal atom, including those gained after sigma donation of electron pair of carbon monoxide molecule, become equal to the atomic number of the next closest inert gases. EAN is equal to A plus 2B, where A equals to the total number of electrons or atomic number of the metal atom and B equals to the total number of sigma bonds between metal atom and carbon monoxide groups, or ligand present in the complex. It is multiplied by 2 since each carbon monoxide or other ligand contribute to 2 electrons. Some examples are as follow. Chromium hexacarbon monoxide EAN value is 24 plus 2 multiplied by 6 is 36 krypton, means krypton having atomic number 36, and EAN rule of um, chromium hexacarbon monoxide is also 36. Iron pentacarbon monoxide is 26 plus 2 multiplied by 5 is 36 krypton. Then tungsten carbon monoxide 6 is 74 plus 2 multiplied by 6 is equal to 86 radon. Then ruthenium CO5 ruthenium pentacarbon monoxide is 44 plus 2 multiplied by 5 is 54 xenon. Dimanganese decacarbon monoxide is 25 multiplied by 2 is plus 2 multiplied by 10 plus 2 for mm1 contribute to electron equal to 72. EAN of each metal atom is 72 divided by 2 is equal to 36 kryptons. Remember, the mononuclear metacarbonyl having odd atomic number do not follow EAN rules. Example, vanadium hexacarbon monoxide is 23 plus 2 multiplied by 6 is 35. Manganese pentacarbon monoxide 25 plus 2 multiplied by 5 is 35. Cobalt tetracarbon monoxide is 27 plus 2 multiplied by 4 is equal to 35. The 18 electron rules. The 18 electron rule was postulated to categorize stable metal complexes. Those complexes which have 18 outer shell electron or where the sum of d electron donated by ligand and overall charge on the complex is equal to 18 are considered to follow this rule and expected to be stable in nature. However, it has been found in several examples which do not follow the rules and several exceptions do exist. Complex with 14 or 16 electron count were also found to be stable. The stability of an octahedral complex, whether following these rules or not, can be rationalized by looking into their molecular orbital descriptions. The most stable arrangement will correspond to a fully occupied bonding molecular orbital. A1G, T1U, EG, and T2G vacant anti-bonding molecular orbital. Thus, this 9 molecular orbital will require a total of 18 electrons. The anti-bonding orbital will be vacant when the energy gap delta 0 between the highest bonding molecular orbital and the lowest anti-bonding molecular orbital is large, which make occupation of anti-bonding Eg star unfavorable. Such complex will follow the 18 electron rules. Particularly, the second and third row transition metal, which do not have more than 18 electrons beyond the core molecular orbital. The largest delta zero splitting is also consistent with strong sigma, donor, and pi acceptor ligand, such as carbon monoxide, PF3, olefin, and arene, which are located at the upper end of electrochemical series. Metal complex energy. Metal complex. Simplify molecular orbital diagram for an octahedral transition metal complex depicting sigma interaction only. A1G EG T1U T2G EG A1G star T1U star. Sigma NS minus 1D NS NP. There are complex having less than 80 electron where the ligands such as chlorine, fluorine do not contribute in extra stabilization of T2G orbital by pi bonding. Example, tungsten hexachloride 2 minus has 40 electrons. TCFe2 minus has 15 electron, osmium hexachloro 2 minus has 60 electron, and platinum hexafluoro minus has 70 electron. We know in spectrochemical series carbon monoxide and nitrogen oxide lies at the higher end as they are good pi acceptor and hence stabilize the T2G orbital. This in turn increased delta zero value and hence octahedral complex with carbon monoxide and nitrogen oxide ligand are mostly found to follow the 18 electron rule. Generalizing, we can say the electron rich orbital in low oxidation state and ligand that are good pi acceptor adhere to the 18 electron rule. Having more than 80 electrons in certain complex can be attributed to small delta zero and so occupation of Eg star orbital is probable. Example, cobalt hexa echo 2 plus has 19 electron. Nickel tris diethynyl amine 2 plus has 20 electron. Copper hexaamine 2 plus has 21 electron and zinc hexaamine 2 plus has 22 electron. Counting of electron in complex. To count the number of electrons in the complex, there are two popular methods. V is neutral atom method and oxidation state method. Here we will be discussing only neutral atom method as it is easier to follow. For this we need to know the number of electrons each ligand donates to the metal in the complex. Table 5.1. Metal is taken as in zero oxidation state in this method. Overall charge on the complex is also considered. An overall positive charge say plus x will be subtracted, whereas a negative overall charge of say minus y will be subtracted from the total electron count. Electron donated by various ligands. Carbonyl electron donated to mu carbon monoxide rigid carbonyl 2 carbon M double bond Cr2 2 phosphine M Pr3 2 mu phosphide MPr2M is 3 amine MNR3 is 2, amide MnR 2 1, mu amido MnR 2 M3, hydrogen MH, electron donated 1, dihydrogen electron donated 2, dinitrogen N double bond N is donated electron 2, isocyanide MC double bond triple bond NR is donated electron is 2, halide MX is 1, mu halide MXM donated electron is 3, alkyl MR donated electron is 1, aryl MR donated electron is 1, thiolate MSR is donated electron is 1, alkoxy MOR is donated electron is 1, mu alkoxy MORM is donated electron is 3. Acyl MC double bond OR donated electron is 1, nitrosyl linear MN double triple bond O donated electron is 3, nitrosyl bend donated electron is 1, alkene sidewise N2 donated electron is 2, alkyne sidewise N2 2 or 4 if it function as pi electron donor. Mu alkyl MCr3M donated electron is 1, mu alkyne bridging donated electron is 4, N1 allyl donated electron is 1, N3 allyl donated electron is 3, N1 cyclopentadienyl donated electron is 1, N5 cyclopentadienyl donated electron is 5, N6 benzene donated electron is 6, N7 cycloheptatrienal donated electron is 7, NH cyclooctatetraenal donated electron is 8, mu indicate bridging ligand, nu indicate hapticity of the ligand. Determination of total number of bond in a cluster. First, determine the total number of valence electron in the complex. That is the number of valence electron in the metal plus the electron from each ligand plus the charge. Say it come out to be X. Now suppose N is the number of metal in the complex. Subtract X from N star 18 electron, N star 18X. Suppose the value come out to be Y. The Y divided by 2, that is Y divided by 2, gives the number of metal-metal bonds in the complex X divided by N, give the number of electron per metal atom. Now if this number comes out to be 18, it implies there are no metal-metal bonds. For 17 there will be one metal-metal bond, and it is 16. There will be two metal-metal bond, and so on. Stepwise determination of number of bond. E3CO12 number of metal atom is 3. Total valence electron 8 multiplied by 3 is plus 12 multiplied by 2 is 48. Y is equal to N multiplied by 18 minus X. 18 multiplied by 3 minus 48 is equal to 6. Bond Y divided by 2 is 3. Number of bond per metal atom 18 minus 48 divided by 3 is equal to 2. Theoretical structure is 3Fe. Nu 5 CpMoCO2 2. Number of metal atom is 2. Total valence electron 5 plus 6 4 multiplied by 2 is 30. Y is 18 multiplied by 2 minus 30 is equal to 6. Bond is Y equal to 2 is 3. Number of bond per metal atom 18 minus 30 divided by 2 is 3. Theoretical structure MO triple bond MO. N4 C4H4 2Fe 2 Fe2CO3. Number of metal atom N is 4 multiplied by 2 plus 8 multiplied by 2 plus 2 multiplied by 3. 18 multiplied by 2 minus 30 equal to 4. So M dash M bond is 2. So number of bond per metal atom 18 minus 30 divided by 2 is Fe triple bond Fe. Now asterisk mark represent mathematical operation multiplication. 18 electron rules allow predicting the number of bond. It, however, does not give any information about bridging or terminal carbonyl. Structure of some common meta-carbonyl complex are depicted in figure 5.4. Nickel tetracarbon monoxide, iron pentacarbon monoxide, chromium hexacarbon monoxide, CO2 octa, diocta, hexa, octacarbon monoxide, Mu2 bridging major, dicarbonyl octacarbon monoxide terminal minor, Mn2CO10, dimanganese decacarbon monoxide, diiron nonane carbon monoxide, triosmium dodecan carbon monoxide, tetrairidium 12 carbon monoxide. Chemical structure of some common metal carbonyl complex. Vibrational spectra of metal carbonyl. Vibration spectroscopy is one of the most commonly used methods of characterizing metal carbonyl. Infrared IR spectroscopy or vibration spectroscopy deal with absorption of energy in the infrared region of the electromagnetic spectrum. Carbon monoxide vibration of a carbonyl group is denoted as UCO and is observed at 2143 per centimeter. In the free carbon monoxide molecule, this frequency absorption change as the coordination CO coordinate with the metal atom. It may shift upward or downward. The change in the frequency directly depend upon carbon monoxide bond length, bond order, and inversely vary with the strength of pi-back bonding between metal and carbon. The acceptance of electron in pi star orbital has a significant effect and decrease the bond order and hence the bond strength. Here are some of the factors which affect the number of carbon monoxide band observed and VCO. Charge on the metal center and role of other ligand. The negative charge on metal center or presence of another ligand with greater sigma donation and poor pi accepting behavior will decrease the carbon monoxide stretching frequency, whereas the increase of a positive charge on metal center and poor sigma donation and strong pi accepting behavior will increase the carbon monoxide stretching frequency. As the electron density of metal increase, more pi back bonding to the carbon monoxide ligand takes place. As more electron density goes into the formerly empty pi star interbonding orbital, the carbon oxygen bond further weaken, but metal carbon monoxide bond strengthen, making it more double bond like in nature. Table 5.3 example AgCO plus has PCO and 2204 per centimeter nickel tetracarbon monoxide has VCO is 2060 per centimeter and cobalt tetracarbon monoxide minus has VCO is 1890 per centimeter. Vibration frequency of carbon monoxide ligand in some common complexes compound. Titanium hexacarbon monoxide is frequency is 17481 per centimeter. Vanadium hexacarbon monoxide 1859 per centimeter. Chromium hexacarbon monoxide 2000 per centimeter. Manganese hexacarbon monoxide 1 plus is 2095 per centimeter. Iron hexacarbon monoxide 2204 per centimeter. Coordination of carbon monoxide to metal itself decrease its vibrational frequency from 2143 per centimeter. That is for free carbon monoxide due to the pi back bonding between empty metal orbital of pi symmetry with anti-bonding pi star orbital of carbon monoxide. This results in increase of metal carbon monoxide bond, but a decrease in carbon oxygen bond. The coordination of other ligand which compete with carbon monoxide for pi back bonding will decrease to frequency carbon monoxide. Bonding mode. The number and intensity of carbonyl bands observed depend on the number of carbon monoxide ligand present of the symmetry of complex. As the carbon monoxide bonding is shifted from terminal to bridging, mu2 or mu3 bridging, the VCO goes on decreasing. Figure 5.5. Carbon triple bond oxygens. Free frequency 243 per centimeter. Oxygen triple bond carbon metal terminal. Frequency 21201850 per centimeter. Mu2 bridging per frequencies 1850 to 1720 per centimeter. Mu3 bridging frequency 1730 1500 per centimeter. Depicting of various bond mode exhibitor of carbonyl ligands. Ligand donation effect. As mentioned before, the ability of ligand to donate electron density to metal has significant effect on the overall electron density above the metal centers, which in turn affect the carbon monoxide stretching frequency. For example, two trans pi back bonding ligands will complete for the same d orbital electron density. This weaken the metal ligand pi back bonding by each one of them. If both trans ligands are carbonyl, they will make equally strong bond with the metal. If the trans ligand is a sigma donor, it will increase the metal carbon monoxide bond strength, also allowing for carbon monoxide by back bonding. For example, the pyridine and amine are not strong sigma donor, but they are even poor pi back bonding ligand. Thus, we can generalize that if any ligand say L is trans to carbon monoxide, it is weak pi accepting ligand such as pyridine. Most of the electron density will taken up by the carbon monoxide, hence the stretching frequency will be lower. If the ligand L trans to carbon monoxide is a strong pi donor such as phosphine, the competition of pi electron density increase and hence CO will increase slightly. If the trans ligand PF3, the frequency is almost the same as that of the complex having all the carbon monoxide ligand. This implies that pi accepting nature of PF3 and carbon monoxide similar. Figure 5.6. Frequency 210 per centimeter, 207 per centimeter, 194 per centimeter, 1895 per centimeter. Depiction of ligands donation effects in terms of vibration frequencies. Important reaction of metacarbonyl. Metacarbonyl serve as precursor in the formation of other carbonyl compound. Some of the significant reactions are summarized below. Substitution reaction. The carbonyl ligand can be substituted by other mono and bidental ligand under thermal or photochemical conditions. Ligand that can be used to substitute carbonyls are phosphine cyanides, endonative ligand, chelating ligand, and ethers. Substitution reactions occur through dissociative mechanism except 70 electron metal carbonyl which proceed through associative mechanism. The latter mechanism is rare and incorporate a 90 electron intermediate species. Dissociative mechanism MCON. MCON minus 1 is CO. MCON minus 1 react with ligand, we get MCON minus 1 ligand. Associative mechanism MCON react with ligand. MCON ligand. MCON ligand is MCON minus 1 ligand plus CO. Some example Fe pentacarbon oxide react with C triple bond NR. FeCO3 CnR2 2 carbon monoxide. Nickel tetracarbon oxide react with 4 CnR is nickel CnR4 and 4 carbon monoxide. Dimanganese decacarbon oxide react with for PR3 to form 2 MnCO4 PR3 and 2 carbon monoxide. 2 Fe2CO12 react with 3 pyridine. We get Fe3CO9 Py3 and 3 moles of FeCO5. Bidental ligands can replace carbonyl in multiple of 2. Some bidental ligands and their reaction with metacarbonyl are given below. Please note that O-phenylene bis-dimethylarsine and orthophenylene and throline ligand are abbreviated diars and O-phen respectively. Molybdenum hexacarbon monoxide diur form MoCO4 diur and 2 moles of carbon monoxide. Nickel carbon monoxide, titanium carbon monoxide, O-phen, we get nickel dicarbon O-phen, 2 moles of carbon monoxide. Chromium hexacarbon monoxide react with 2 diur. We get chromium dicarbon monoxide diur 2 and 4 carbon monoxide reduction. Metallic sodium or sodium amalgam are used to reduce metal carbonate to carbonylate anion. Mn2 decacarbonoxide react with 2 sodium to give 2 NaMnCO5. FeCO5 react with 2 sodium Na2FeCO4 and carbon monoxide. CrCO hexacarbon monoxide react with 2 sodium. We get Na2CrCO5 carbon monoxide. In above reaction Mn0 Fe0 chromium 0 oxidized to Mn1 Fe2 chromium 3 oxidation state respectively. Nucleophilic reaction. In the reaction of carbonyl compound with the sodium hydroxide, the hydroxide anion nucleophile attack the carbon monoxide ligand to form metal carboxylic acid, which is followed by release of carbon dioxide to give metal hydride or carbonyl metallase. This reaction is known as Haber base reaction. FeCO5 react with NOH, NaFeCO4COH, NaFeCO4COH, NOH react with sodium hydroxide. We get NaHeFeCO4 and NaHCO3. Protonation of hydride anion with the neutral compounds NaHFeCO4 H plus H2FeCO4 and plus Na plus reaction with electrophiles. Metal carbonyl are relative and reactive towards electrophile. Even though exist in low oxidation state, they do not react with the alkylating agent, weak acid, weak oxidizing agent. However, they have been found to react with halogen as shown in some of the reaction given below. Fe pentacarbon monoxide react with halogen, dihalogen, we get FeCO4X2 and carbon monoxide. Molybdenum hexacarbon monoxide react with chlorine to get molybdenum tetracarbon monoxide and chlorine to give 2 carbon monoxide. Some polynuclear carbonyl undergo metal-metal bond cleavage in presence of halogen. Manganese decacarbon monoxide react with chlorine to get 2 manganese pentacarbon monoxide chlorine. Reaction with nitric oxide. Metal carbonyl react with nitric oxide to give metal nitroside. Fe pentacarbon monoxide. 2 nitrogen monoxide 95 degrees Celsius. FeCO2NO2 3 moles of carbon monoxide. CO2 CO8 plus 2NO 40 degrees Celsius. 2CO CO3NO and 2CO. Reaction with hydrogen. Metal carbonyl can be reduced to hydra upon reaction with hydrogen to give metal hydride. CO2 CO8 react with hydrogen at 165 degrees Celsius 200 atmosphere to get 2 carbon monoxide CO4H. Mn2CO10 H2 react with hydrogen 200 atmosphere, we get 2 moles of MnCO5 hydrogen. Even though the above neutral compounds are called hydride, they have been found to act as proton donor, thus behaving as acid. Mn pentacarbon monoxide hydrogen 165 degrees Celsius 200 atmosphere. MnCO5 minus H plus. CO cobalt tetracarbon monoxide H. So CO tetracarbon monoxide 4 minus plus H plus. And any hydride such as HFeCO4 minus behave as true hydride reducing agent and can reduce alkyl halide. Alkyl halide react with HFeCO4 minus RH. XFeCO4 minus. Transition metal nitroside. The chemistry of transition metal nitroside though gained significant attention somewhat later to that of metal carbonyl, but in present time the work done in this field run parallel to that of metal carbonyl. Nitric oxide or the nitroside ligand can bind to the metal in a manner quite different from the of carbonyl. The two common binding mode of nitroside can be represented as shown below. Linear coordinating mode, band coordinating mode, depiction of linear band coordination modes of nitroside ligands. In the linear binding mode, the nitrogen behaves as 3 electron donor in nitrogen oxide plus, and Mn has a multiple bond character. It donates 1 electron to the metal before donating an electron pair for the formation of coordinate covalent bond. The nitroside nitrogen oxide plus is isoelectronic with carbon monoxide ligand. It is the most commonly bonding observed in the band coordination mode. The nitrogen acts as single electron donor towards the metal and MnO bond angle. is 120 degree. Here the Mn bond is longer than that in the linear bonding mode. It is still somewhat shorter than a single sigma Mn bond distance. In most of the nitrosyl complex, nitrosyl plus nitrosonium ion act as the ligand by donating pair of electron. In some common nitric oxide is also known as exists as an ion, such as in CO plus 3 CN5 NO minus 3 and CO plus 3 NH3 5 CO NO plus 2. The fumed nitroxide has an IS stretching frequency of 1870 per centimeter. The nature of other ligand present in the complex charge and structure of the complex affect the nitrogen oxide stretching frequency. The nitrosyl ligand is linear when it coordinates as nitrogen oxide plus and frequencies observed in the range of 120 and 40 per centimeter. The role of metal nitroxide has been much explored as homogeneous catalyst. They find their biggest application in olefin disproportionation reactions. Dinitrogen complex. Transition metal coordination compound containing dinitrogen molecule nitrogen as ligand is called nitrogen complex. Such complexes are of interest because dry air in Earth's atmosphere contains nearly 78% nitrogen by volume that reflect reluctance of dinitrogen towards chemical reaction in ordinary conditions. Dinitrogen is converted to its organic and inorganic derivative through a process called dinitrogen fixation, which primarily involves the binding of dinitrogen to metal center present in the enzyme nitrogenase, followed by a series of other steps. Ruthenium complex, ruthenium pentaamine dinitrogen 2 plus is the first synthetic complex that containing a dinitrogen ligand. It is an octahedral paramagnetic complex in which 5 of the hexacoordinated sites are occupied by amine ligands and 6th position is occupied by nitrogen molecule nitrogen. The presence of nitrogen as a ligand in this complex causes a strong vibrational band in the FTIR spectra of the compound around 270 to 2100 per centimeter, like acetylene, C2H2, and carbon monoxide. Carbon monoxide molecule dinitrogen N2 also possesses a triple bond similar to the acetylene carbon. Ligand dinitrogen also offer mononuclear terminals and bridging bonding modes. If the nitrogen molecule is shared by two or more metal center in a complex, the manner of bonding is termed as the bridging modes based on the geometric relationship between the nitrogen molecule and the metal center. The complex are also differentiated to have end-on or end-side-on modes. With the figure 5.8 in the end-on bonding mode of transition metal dinitrogen complex, the nitrogen-nitrogen vector can be considered in line with metal ion center, whereas in the side-on mode, the metal ligand bond is known as perpendicular to the nitrogen-nitrogen vectors. Terminal or mononuclear, bridging mode, end-on mode, side-on mode, depiction of various coordination mode of dinitrogen ligands. Dioxygen complex. Dioxygen complex. Transition metal coordination compound containing dioxygen molecule oxygen as ligand or called oxygen complex. As a biological process of nitrogen fixation motivated the study of synthetic dinitrogen complex. Biological oxygen carriers, protein including myoglobin, hemoglobin, hemerythrin, and hemocyanin has inspired the studies pertaining to the transition metal complex of dioxygen molecule. This protein reversibly binds with the oxygen molecule. Hence, reversibly bound oxygen containing transition metal complex are of particular interest for their ability to mimic natural respiratory system. The first synthetic complex was reported in 1930 with cobalt-2 complex reversibly bound oxygen. Oxygen ligand can bind to a single metal center through two coordination mode, namely end-on N1 where the ligand is connected to metal center at one point, Only another one is side-on N2 mode, where the ligand connects to the same metal center through two sites, that is from N2 chelate. End-on N1 mode, side-on N2 mode. Depiction of various coordination mode of dioxygen ligand. Dioxygen derivative of cobalt 2 and iron 2 complex of porphyrin and related anionic macrocyclic ligand usually exhibit N1 bonding modes. On the other hand, N2 bonding modes is the most common motif towards which oxygen ligand coordinate to the metal center. Reacting low valency metal complex with oxygen yield N2 adducts, for example, Vasca complex reversibly bind oxygen as presented below. Binding of dioxygen ligand with Vasca complex iridium react to oxygen. Dioxygen ligands can also bridge two metal center at once as in case of the hemocyanin. Each of the oxygen atom of bridging dioxygen's ligand can bind either to one metal center each or N2 chelate the metal center. Hence, there are three possible bonding modes, namely mu2 N1, N1 mu2 N1 N2, and mu2 N2 N2. The exact bonding mode is often characterized by the X-ray crystallography studies. Mu2 N1 N1 mode, mu2 N2 N1 mode, mu2 N2 N2 mode, various binding modes of dioxygen ligand. Tertiary phosphine as ligand. Phosphines are two electron donor ligands which coordinate through the lone pair of electrons available on the phosphorus atom. Phosphine ligand, particularly triphenyl phosphine, is an excellent ligand. Ligand acid shows good solubility in organic solvent and tend to bind with transition metal in a range of oxidation state. Important example of triphenyl phosphine containing metal complex include Vasca complex, Wilkinson's catalyst RFPH3PCl Grubbs catalyst, and PDPH34. Vasca complex Wilkinson catalyst tetrakis triphenyl phosphine palladium 0 PDPP3H4. Benzylidine bis tricyclohexyl phosphenone dichlororuthenium Grubbs catalyst. Triphenyl phosphine complex are prepared by the treatment of metal halide, where triphenyl phosphine depicted below for the synthesis of bis triphenyl phosphine palladium 2 chloride PDCl2N react with 2N-PPH3 to get N-PDCl2-PPH3 2. As stated earlier, phosphine molecules are two electron donor, that is Lewis base which interact with metal center as sigma donor ligand. Additionally, phosphorus atom possess empty d orbital as well. As a sigma star anti-bonding orbital, those can accept electron density from filled d orbital available in metal center. This back bonding causes tighter binding of metal and phosphine ligands. R3p filled sigma orbital metal vacant d orbital appropriate symmetry. P gives electron m bonding interactions. Vacant sigma star orbital filled d orbital appropriate symmetry. M give electron to p back bonding interaction. 5.13 Schematic depiction of bonding and back bonding interactions in transition metal complex comprising phosphine ligands. Phosphine complex are mainly used as a catalyst for organic conversion. Wilkinson catalyst is used for hydrogenation of olefin with molecular hydrogen. The mechanism of hydrogenation of olefin catalyzed by Wilkinson catalyst involve initial dissociation of 1 or 2 ppH3 ligand to give 14 or 12 electron complex respectively. The initial step is the oxidative addition of hydrogen to the complex center, which further followed by pi complexations of alkene. Migratory insertions, reductive elementary yield the formation of alkene as depicted in figure 5.14. Schematic depiction of mechanism of hydrogenation of alkene catalyzed by Wilkinson catalyst. Summary. This chapter provides an account of important aspects of organometallic chemistry, particularly in context of metal carbonate. Several methods of synthesis and chemical reactions for carbonate are presented in this unit. Molecular electronics, Structure aspects have been discussed to make students understand the basic of bonding in carbonyl and other organometallic complex. Data on an implication of effective atomic number rules and 80 electron rules are also presented. Later section of chapter elucidate the important aspects of transition metal compound nitroxide and nitrogen dioxide and triphenyl phosphine ligands.